All right, so constant rate of change and proportionality. That's the next portion of our functions unit, where we're talking about linear functions, linear relationships. Now, if you think of the word linear, what word do you see inside of that term linear? Line, right? The word line is inside of the term linear. And that's because linear relationships form a straight line when you graph them, because of the fact that they have what's called a constant rate of change. So let's go ahead and highlight or underline the word linear and the fact that they have a straight line when they are graphed. Straight lines when they are graphed. And it's because they have a constant rate of change. And I'm going to go ahead and label that as CRC. A constant rate of change is also known as the term slope, aka slope. Now we're going to talk more about slope in a couple of days. Maybe tomorrow or Wednesday we'll talk more about what slope is. And how to identify slope with linear relationships. But linear relationships must have a constant rate of change. And how you're able to identify that constant rate of change is by finding what the constant change in y is, and then placing it over, so you're creating a fraction, you're going to place it over the constant change that occurs in your x. Okay, the constant change of your y over the constant change of your x. That's what makes these relationships linear or forming a straight line. Now, it's important to understand a couple of things when we talk about, because when we're looking at constant rate of change, we're going to be looking at them in table format. We're going to be looking at them in word problem format, equations, and in graphs. But what we're going to focus on for today are tables and graphs. So when we look at table relationships, you can have either a vertical table or you can have a horizontal table. To keep in mind, when we're looking at vertical tables have your x values usually on the left side, and the y values are usually on the right side of a vertical table. And then when we're talking about horizontal tables, we usually put the x value on the top and the y value on the bottom. Okay, sometimes, very rarely, but sometimes they might reverse those. So you need to make sure you're paying attention to what the labeling is. It's also important to understand that when we're looking at a graph, guys, how do you read? What direction do you start from and move towards when you're reading just a normal book? Alex? Left to right. So when we do the same thing for a graph, you read a graph from the left side of the graph to the right side of the graph. Sometimes the graph might start at the top and work its way down. Sometimes it might start at the bottom left and work its way up. But you always start on the left side of the graph and read it to the right side of the graph. So write that down as well. You read a graph from left to right. You always read a graph from the left to the right. And again, it might start at the top left and work its way to the bottom right, kind of like when we're reading a book. We start at the top left and we read until we get all the way down to the bottom right hand. Or it might start at the bottom left and work its way to the top right. It's always left to right though. Okay, some other important things to make sure you keep in mind when we're talking about relationships for x's and y's. Something that you might want to make sure you remember is time is always an x value. Time is always going to be an x value. Money or distance is y. Or our y values, use proper English, our y values. we talk about time, time is always related in the x value. If we talk about money or we talk about distance, that's usually going to be our y values. So when you're seeing relationships like that, that are utilizing those labelings, those quantities, then you should note that they go for the x and which ones go for the y. Okay? Now, let's take a look at a couple of examples here. So for example number 1, talking about a table, we're wanting to identify what the relationship is if this has a constant rate of change, and if it does have a constant rate of change, then that means it's going to be a linear relationship. So we're trying to identify if it's linear by identifying the constant rate of change first. Okay? So looking here, again, time, hours, is going to represent our x value. So I'm going to write an x up above the hours. What we're being charged, money, that's going to represent our y values. Now when they're talking about the change that occurs in the y's and the change that occurs in the x's, that means you're going from one point to the next and seeing how are you increasing or decreasing from one y value to the next or from one x value to the next. And that creates that rate of change, that constant rate of change. So CRC again, because that represents constant rate of change. I abbreviate it, makes it easier. You're setting it up as a fraction where you're identifying that change in the y over that change in the x. You're identifying the change in the y over that change in the x. So I first want to start with my y's. How are my y's changing? So I'm going from 10 to 18. What am I doing? Am I increasing or decreasing? Increasing. So I'm going to put a plus sign because it shows that I'm increasing. And what am I increasing by? 8. Okay? What about from 18 to 26? Increasing by 8. From 26 to 34? Increasing by 8. So this is my change of y. What I just did right here represents the change that occurred in my y's. I'm consistently increasing by 8. So I'm going to put a positive 8 at the top of my fraction. Then I'm going to do the same thing for my y, or for my x's. I'm going from 1 to 2. What's happening? Plus 1. From 2 to 3. Plus 1. From 3 to 4. Plus 1. This represents that change of my x. What I just identified here is the change of my x. So I'm going to put a plus 1 underneath it. Okay? A positive over a positive equals a positive. So that means that my constant rate of change is 8 over 1, or $8, because this represented money, per 1 hour. $8 per 1 hour. And since it had a constant rate of change, this makes it a linear relationship. Because of the fact that it has a constant rate of change, it is a linear relationship. Now, you do the exact same thing when it comes to a graph, except instead of having a table format, you have x and y values in plotted form. So we've got a point located here, here, here. These are 3 points that I've got located. Again, you start from the left side and work your way to the right side. So we're starting with this top point up here, and I want to identify how the y is changing each time first. We want to identify the change in y. The y value, is it left to right or up and down? Your y-axis, left to right or up and down? Up and down. Your y-axis is what moves up and down. Your x-axis is what moves left and right. So when I'm going from one point to the next for the y's, I want to see how my vertical is changing. So This represents the change of my y, just that vertical line drop. Same thing here, a vertical line drop. That represents the change of my y. Am I increasing or decreasing? Decreasing. It's going down. So I know it's going to be a negative. What is it decreasing by from one point to the next level? 20, right? It started at an 80 and then it went down to a 60. So it decreased by 20. Same thing for here. It started at 60 and went down to the level of 40. So it decreased by 20. So that means, and here I'm going to zoom in so it's easier for you guys to see. That means that my constant rate of change had a change in my y of negative 20. It had a change in the y that represents negative 20. Now we got to do the same thing for the x. So the x represents that horizontal run. So we're going from here to here. And then same thing on this level from here to here. Is it increasing or decreasing? Increasing, right? It goes from left to right. So it's moving in a positive direction each time. So I'm going to put a plus sign. And then going from this point to the next point, what am I increasing by? 8. You got to look at your axis from this point, which was at the 8, to the next point, it goes to the 16. It moves by 8. Then we're going from 16 to 24. It's also moving by 8. So that means that the change of my x is an increase of 8. So we have a negative over a positive. A negative over a positive is just going to equal a negative. So I'm going to put a negative sign. And we can simplify 20 over 8. What are they both divisible by? 2 and 4, right? 4 is the largest, so let's divide them both by 4. If we do so, that comes out to a negative 5 over 2. And of course, you always want to relate it back to what the labelings are. What did y represent in this case? Time. So they did theirs a little bit different, didn't they? They made their time represented by y, which isn't typical. And then they made their x representing volunteers. Okay? So be mindful. Like I said, typically speaking, time should have been an x. But be mindful of what they label the graphs as. You always want to relate it back to what the graph says. Okay? When you create your graphs, you should always put your time on the bottom. So the constant rate of change in this case is going to represent a decrease of 5 minutes per 2 volunteers. Now, because we had a constant rate of change, that means that it is a linear relationship. It is a linear relationship. If you wanted to put a negative 5 there, that's fine. If you put decreases by 5 minutes, or you can put negative 5 minutes for 2 volunteers. Okay? I want you guys to try problem C on your own. Try problem C on your own. Let's take a look here. So the first thing that we want to identify when we're trying to see if there's a constant rate of change is we want to identify the change that's occurring in the y. So who can tell me what is occurring here with the change of the y's? Armando? Okay, minus 5. Minus 4. And then minus 4. Okay, so this is the change that is occurring in the y. What about for the change of the x? Who can tell me what the change of the x is? Bridget? Okay, plus 5, plus 5, plus 5. So is there a constant rate of change? No, because if we're taking a look here, we have two different values that's going to be occurring. We have a negative 5 over a positive 5, which that would simplify down to a negative 1. And then we have a negative 4 over a positive 5, which that would simplify down to a negative 0.8. Okay? Not the same things. So since there is no constant rate of change, then this is nonlinear. If there isn't a constant rate of change, then that means that the graph is not linear. Now, I don't want you thinking that just because there's no consistency in the y, then that means there's always going to be no constant rate of change. Notice what I did is I compared each of the changes together to make sure that they weren't the same. Now, it's obvious that they're not the same when you've got a non-consistency with one value but consistency with the other. But that's not always the case. Take a look here. I wrote down a couple different examples. Look at this x and y. I want you to go ahead and write this x and y values in a table right below. You should be able to put that in real quickly. So we have x values being at 0, 2, 3, and 6. And then we have y values at 2, 8, 11, and 20. If I take a look at the change of my y's, first I'm increasing by 6. Then I'm increasing by 3, and then I'm increasing by 9. So I have y values of a positive 6, a positive 3, and a positive 9. They're all different. So now I look at my x's. For the change of my x, I'm increasing by 2, then I'm increasing by 1, and then I'm increasing by 3. So a positive 2, a positive 1, and a positive 3. So I now have 6 over 2, 3 over 1, and 9 over 3. They all simplify to the same thing. They're all equal to each other. 6 over 2 simplifies to a 3. 3 over 1 simplifies to a 3. 9 over 3 simplifies to a 3. So because they're all equal to each other, then this makes it a linear relationship. So again, just because you don't see consistency in the change does not mean that it's not linear. You have to check them as each individual ratio. If each individual ratio is equivalent to each other, simplifies to the same value, then it is linear. If they still don't simplify to the same value, it would be nonlinear. Okay, I want you to try that with this graph or this table. Here's your x and y values. Your x is at 17, 9, 4, and 1. Your y value is at 47, 23, 8, and negative 1. Identify if it's a linear relationship or not by seeing if it has a constant rate of change. All right, let's take a look at it. What are the values of change for the y? Ray, what did the y values change by? To go from 47 to 23, 23 to 8, 8 to negative 1, what was the changes that were occurring? Okay. And then from 23 to 8? And then from 8 to negative 1? Very good. Okay. For the changes of our x's to go from 17 to 9, 9 to 4, and 4 to 1, what was the change for that, John Michael? Negative 5, okay. Negative 3. Okay, so again, there's no consistency here, but we need to check them each individually. So that means we're going to set it up as negative 24 over negative 8. We're going to set it up as negative 15 over negative 5, and then negative 9 over negative 3. When we simplify them all, do they come out to the same value? Yes, they all come out to a positive 3. They are all equal to each other. They all equal a positive 3. So that means that this is a linear relationship. So you have to check them all individually before you can determine if it's linear or not. Any questions so far? Okay, so again, it's important. If it's linear, it's going to form a straight line, and it has a constant rate of change. Straight line, constant rate of change is linear. Now we're going to talk about some proportional relationships. In order for it to be a proportional relationship, not only does it have to be linear, but it has a very specific point that it has to encounter, and that point is the origin. What value represents the origin, guys? 0, right? 0, 0. So real quickly, I want you to make sure you identify that when we talk about proportional relationships, in order for it to be proportional, and here I'll highlight that in orange so it's easier to see. In order for it to be a proportional linear relationship, it has to be a straight line, and it must pass through the origin. Which is at 0, 0. The origin is 0, 0. Proportional relationships are always going to be linear relationships. They have to have a 0, 0 starting point. Okay? So for here, we want to determine if this is a proportional relationship based off of the table. And then we also want to graph it. So we want to showcase what it looks like as a graph. So as a graph, it should be a straight line, and it should be passing through the point 0, 0. So when we're taking a look here, we're talking about the speed over time. Speed that's occurring over time. Okay, now be mindful, like I said, majority of the time I said that our tables would be set up as x over y. Is that the case here? No. This is not the case here. In this situation, they place the y on the top, they place the x on the bottom. So please be careful about that. You need to make sure that you have an understanding of what's supposed to be labeled what. So our time is going to be relevant to here on the bottom. And then speed is what's going to be the y-axis. So I'm going to go ahead and get those labels created right now. So I want to know what my constant rate of change is going to be because I need to know if it has one. If it has a constant rate of change, then I definitely know that it's a linear relationship. It's the first thing I want to check. So here, for my change of my y, each time that I'm going from one point to the next, I'm increasing because it's getting larger, and I'm increasing by 9.8 every single time. Every single time I'm increasing by 9.8. My x-axis, my x values are increasing each time as well, and they're increasing by a value of 1. So do I have a constant rate of change? Yes. Okay, my constant rate of change is going to be 9.8 over 1. So that means that it is a linear relationship. So we're good so far. We do have a linear relationship. Now I need to know, did I start at 0, 0? Did I have a point at the origin? Yeah, look at my very first starting point, 0, 0. So it starts at the origin. So that means that this is a proportional relationship. It is a proportional relationship because it was linear and it started at the origin. So now we're going to graph it. I know that my point 0, 0 is located here. I'm going to go ahead and skip every other line when I'm graphing my point. So that's going to be a 1, 2, 3, 4, 5, 6, and 7. You don't have to do that like mine if you don't want to, but I'm just choosing to do so. And then for my y-axis, I know that I'm going to have to go all the way up to 49. It's a good idea to be able to go past that. So I want to see how many lines I actually have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines. I have 14 lines. So if I did 14 times 2, then I would only be able to get all the way up to 28. If I did 14 times 3, I would only be able to get up to 42. I need to make sure I'm able to get past 49. So that means I'm going to go ahead and make each line count by 4s. 14 times 4 is going to put me up to 56 up here. That gets me well past my last point that I need to graph. Everybody understand how I did that? Okay, so that means each of my lines is going to be worth 4. This is how typically we come up with what our labels or our axes are going to be representing. Each are intervals. So we're going to count by 4s. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, and 56. So it gets me up and well past that 49 mark. And now I just need to graph each of the points. So we already graphed 0, 0. Now I'm going to graph 1 and 9.8. 9.8 is going to be just a little bit above the 8. It's not going to be directly in the center because directly in the center should be 10. So we're just going to do very slightly below the center. It's not going to be perfect, and that's okay because it's decimal values. It's not going to be the perfect representation. Okay, at 2, we go up to 19.6. That's very close to the 20 mark. At 3, we're at 29.4. That's almost at the 30 mark, which would be almost halfway between 28 and 32. At 4, we're going up to 39.2. Again, that's almost at the 40 mark. And at 5 minutes, or 5 seconds, I guess 5 seconds, it's going to be at 49. So that is a little bit above the 48. And there's my graph. I'm going to go ahead and, as always, use a straight line. If you've got a ruler, use a ruler. If you don't have a ruler, use like a notebook or an index card, something with a straight edge to it to graph the points. It's linear, so it's a straight line. Starts at the origin, so it makes it proportional because it's straight and origin. Okay. I want you to do the exact same thing on the back. On the back, you've got hours spent studying, so that's time, and test scores. That would be your Y. And then the second graph is representing the weight of a dog, or sorry, not weight of the dog, but the weight of an item, and then the mass of the item. The weight versus the mass. So you're comparing those. You're going to identify if it has a constant rate of change, and will it start at the origin. Even if the table doesn't start at the origin, doesn't necessarily mean that it can't go through the origin. You would just have to extend. If it's a linear relationship and it can go through the origin, then it would be proportional and graph the representations. Okay, let's go ahead and go over this. So for the hours studying and test scores, this is not a proportional relationship. It does have a constant rate of change if we do look at how the hours are changing versus the test scores and changing. The test scores are increasing consistently by 16 as the hours are consistently increasing by 1. So that means it does have a constant rate of change, making it linear. So it is a linear relationship. However, it isn't able to pass through the origin. Okay? It would not be able to pass through the point 0, 0 and maintain its linearness. It wouldn't be able to do so. Another way of thinking about how to look at it if you weren't to graph it is think about the table if it were to go backwards. So right now, yeah, I can graph it and then I can extend my graph until I pass the y-axis and see if it passes through the origin in that fashion, which it doesn't. It doesn't pass through the origin. But if I didn't have the ability to graph, I could look at just the table itself. Right now, as I'm moving from left to right on my table, so I'm going to, instead of drawing just these little loops, I'm going to draw these arrows to show that I'm going from 52 to 68. I'm going from 68 to 84. I'm going from 84 to 100, and I'm increasing or adding 16 each time. Same thing for here. I'm going from 1 to 2. I'm going from 2 to 3. I'm going from 3 to 4. So I'm moving in the direction towards the right. But what if I were to go backward? Instead of me increasing by 1 to go forward, if I went backward, I would subtract a 1. And that would bring me to 0. And then instead of going forward and adding 16, I would go backwards and subtract 16. And that would bring me to what? If I do 52 minus 16, what would that bring me to? What's 52 minus 16? 36. Is that 0, 0? No, one of the values is at 0, but the other value is at 36. That's not the origin. So write that down. That is not the origin. In order for it to be the origin, it would have to go back 0, 0. But in the manner of rate of change that it's moving by, it's not allowing us to go to 0, 0. Which is why when we graph it, if I extend my graph also extends down to 0 and 36. So whether you're graphing it and seeing if it passes through the origin, or if you're just moving in the opposite direction, utilizing that constant rate of change to move backwards until you get to a point of 0 something, whether it's 0, 0 or 0 and another number. Okay, so this makes it not proportional. Same thing here. For the next problem, this is a proportional relationship because, again, it does have a constant rate of change. My x is consistently increasing by 20s, while my y is consistently increasing by 9. So 9 over 20 makes it a linear relationship because it has a constant rate of change. And it does pass through the origin if I were to extend the graph towards the y-axis. But if I do the exact same thing, instead of moving forward, if I move backward, to move backward, I would subtract a 20. And to move backward in this direction, I would subtract a 9. What's 20 minus 20? 0. And what's 9 minus 9? 0. So we are able to get to the origin. So if your table does not provide a point of 0 something, then you can find that point yourself by just moving backward. Since it will pass through the origin, it does make it a proportional relationship because it's linear and goes through the origin. What if it wasn't linear? What if it went through the origin but it wasn't linear? Would it still be proportional? No. It must satisfy both conditions. It has to be a straight line. It has to go through the origin. Any questions? Okay, what you're going to do is you're going to log into Google Classroom and you're going to work on 3 IXLs.